Okay, welcome everyone. We'll wait just a second for a couple more people to arrive. Who can tell me what I am screen sharing?
Geodesics and the model discussed.
Say it again.
Geodesics and the Poincare and Klein model with Ken.
That is absolutely correct.
Polygons.
So on the left, there's a tessellation of the Poincare disk, and those round-looking curves are actually straight lines. On the right, there's exactly the same configuration viewed in the Klein model. Maybe somebody else can tell me, what tessellation is this?
Is it like 2, 3, 7 triangles?
Exactly. So there's this triangle here is almost like a 30, 60, 90 triangle, except this top angle, the center of the pink heptagon has, obviously it's not pi over 6, it's pi over 7. And whenever you have a triangle whose internal angles are of the form pi over n, you can reflect it through its sides and it gives you a tiling of hyperbolic space. And this is a very famous tiling. It turns out to be the densest possible tiling of hyperbolic space. And what's a little hard to see, I think, going back and forth between the two models, in the Poincare model on the left, you can see pretty clearly that 14 of these triangles fit together around a vertex to make a regular heptagon, a 7-sided figure. It's a little bit harder to see in the Klein model. It took me a while to trace it out exactly. You get distracted. But the corresponding heptagon is in blue on the right. And you see this tendency of the Klein model to sort of push all the information to infinity. So concentrating on the Poincare model in terms of visualizing hyperbolic space, what you want to get into your mind is the idea that all these little configurations near the boundary are of the same size as the configurations in the middle of the figure. They look smaller because of perspective, but they're just receding towards the horizon, which is this round circle. Okay, so we'll discuss that particular group in more detail later today. But let me start by amplifying the discussion of the various homogeneous spaces for our isometry group G. So we're dealing with hyperbolic geometry, so G is our isometry group. And we saw that as a Lie group, this is isomorphic to SL2R, except you have to remember that minus the identity X by the trivial Mobius transformation. So we mod out by that. And then we were able to identify the upper half plane with G mod K, where K was the stabilizer of I in the upper half plane model. In other words, it's the set of matrices of the form cosine theta, sine theta, minus sine theta, cosine theta. You might call this E theta, parameterized by theta in the circle, which is R mod 2 pi z. So this compact subgroup is isomorphic itself to a circle inside of G. By the way, I will always write matrices, but you have to remember that we're modding out by plus or minus the identity. So if you were to look at E pi here, let's see, the cosine of pi is -1. So this would be here, but this it acts by the identity on the upper half plane. So actually E theta is rotation by angle 2 theta around the point I in the upper half plane. Okay, now inside of G, there are two other types of subgroups that are generated by a single element of the Lie algebra. That is, two other types of one parameter subgroups. And they can be conveniently normalized as follows. One of them is called A. So this will be the set of transformations, let's say AS is e to the s over 2, 0, 0, e to the minus s over 2, where s is in the real line. So this is not a circle, it's a non-compact group isomorphic to R. And it has the property that if you apply AS to I, you get e to the s times I. So in other words, let's have some pictures associated to these groups. So here's the upper half plane, and here's the, well, what that point is split line is for. Here's the imaginary axis. Here's the point I. So K was the stabilizer of I. A is the stabilizer of this geodesic gamma that runs from 0 to infinity, and preserving its orientation. And indeed, AS is just translation by distance S in the hyperbolic metric. So in any case, this is isomorphic to the stabilizer of gamma. And then our third one parameter subgroup is N, which is the elements I'll write as NT, 1, T, 0, 1. Again, T is in R. This is a non-compact one parameter subgroup. And of course, this acts by AT of I is I plus T. So it doesn't move along a geodesic, rather, it moves along this horizontal line here. So this object, which I'll call H, is the, actually let me call this eta. This is the object that's stabilized by N, and gamma is the object that's stabilized by A. What is this object eta geometrically?
Is it a horocycle?
Yeah, that's right. So this is the, so to speak, the circle of infinite radius. Okay, so now it's an easy fact that every one parameter subgroup of G is conjugate to either K, A, or N. So if we wanted to form, if we want to look for geometric objects, they should have to do with the orbits of these spaces. And in terms of one parameter group, this is everything that can happen. And that's easily verified if you have an elliptic transformation, it belongs to a conjugate of K. If you have a hyperbolic transformation, it belongs to a conjugate of A. And if you have a unipotent transformation or parabolic transformation, it belongs to a conjugate of N. So these three groups and these specific forms for them will play a big role in the sequel. Now there's one other group that you can form here that's also very interesting, which is the group AN. You see, A normalizes N. That is, let's put Z here. AS of Z is just multiplication, and this should have been NT. NT of Z is just addition. When you put addition and multiplication together, you just get the affine group. So AN, if you like, it's the set of transformations. Z goes to AZ plus B. It's a solvable group with N as a normal subgroup. It's a two-dimensional subgroup of G, whereas these three are one-dimensional. And we can make a little theorem here, which I'll just sneak in here. In fact, the connected subgroups G up to conjugacy are, in fact, the identity KAN, AN, and G itself. Okay, so to each, and so what is the geometric object that's stabilized by AN? So AN doesn't fix, this group doesn't fix any point in the upper half plane. Well, even N doesn't do that. But what it does do is it fixes the point at infinity. And so this we can think of as the stabilizer of the point at infinity in the boundary of the upper half plane. Okay. So these groups will play a leading role in the sequel, and you can see that each group is associated to a different type of geometric object. K, what corresponded to the points in hyperbolic space, and since G acts transitively on hyperbolic space, we can identify hyperbolic space itself with G mod K. Now what about A? Well, A is the stabilizer of this oriented geodesic. And since the stabilizer, since G acts transitively on oriented geodesics, G mod A can be identified with the space of all geodesics. So G mod A is what I was calling G before. It's the set of oriented geodesics in hyperbolic space. And we saw that one model for this space is it's the one-sheeted hyperboloid in the Minkowski model. We'll give another model in just a second. And what about this space N? N is the stabilizer of a horocycle. So G mod N is what I call L for light cone. It's the set of horocycles, all horocycles in the upper half plane. And it can also has a nice picture in the Minkowski model. It's one component of the light cone. But it has an even simpler model, which we can attain in the following way. What does SL2R most naturally like to act on? What is the space you usually think of SL2R as acting on?
The plane?
R2.
The plane, R2, the vector space. It's 2 by 2 matrices, so it acts linearly on the plane. It almost acts transitively. The only problem is you can't send the origin to something other than the origin. So SL2R acts on R2 minus 0, and so there should be a space which is the quotient. There should be a homogeneous space for SL2R, which is just R2. And indeed there is, and it's nothing more than G mod N. This is the same thing as R2 minus the origin. Because this group of matrices, it's just the matrices that have 1, 0 in the first column. So it's the stabilizer of a vector in R2, the standard vector on the x-axis. Once you know this is 1, 0, the only way you can complete the matrix is ST1 for some other TNR. But there's one small nuance, which is this plus or minus the identity. So the light cone, or the space of horocycles, is almost the same as the plane with SL2R acting linearly. We just have to remember that, in fact, you identify vectors with their negatives. Okay, now what is the space G mod AN? This is going to be different. These spaces were two-dimensional because we were taking the quotient by one-dimensional subgroups. G is three-dimensional. H itself is also two-dimensional. But AN is a two-dimensional solvable Lie group. So that homogeneous space is going to be one-dimensional. And what is it? Well, this is the stabilizer of a point on the boundary of hyperbolic space. And again, G acts transitively on the boundary of the upper half plane. And so G mod AN can be identified with the boundary of hyperbolic space, which is sometimes written as S1 infinity because it is topologically a circle, and also it's at infinite distance from any point in hyperbolic space. in the upper half space model, it's concretely the real line with infinity added. In the disk model, it's concretely the boundary of the unit disk, which is just the unit circle. Okay, now there's one piece of interaction between these homogeneous spaces that's especially nice that I want to point out to you. Namely, to specify a geodesic, all we have to do is say where it begins and ends. So we specify 2 points on the unit circle, and we have a geodesic. So this space, G mod A, can also be identified with the space of ordered pairs of distinct points on the circle at infinity. So this is also naturally the same as S1 infinity cross S1 infinity, but with the diagonal removed. I'll just call that delta. So to every point in the one-sheeted hyperboloid, you should be able to naturally associate some points at infinity. Also, we can also identify this the circle at infinity with the space of horocycles, because at every point on the boundary you have a horocycle, but it's not quite unique. You have many concentric horocycles, and those correspond to a single ray in the light cone. So the circle at infinity can itself be thought of as the light cone modulo scaling. So modulo the action of R plus. Of course, it's a further quotient of G mod n. It's G mod n mod A. And A is this scaling factor here. Okay, so associated to hyperbolic space, there's not just one space. The upper half plane, there's actually 5 spaces. And there's one space for each of these groups here. Well, I guess we can leave out the identity, K, A, N, A, and G. Oh, wait a second. What about G itself? What is the homogeneous space associated to G? If I want to think of the Lie group G geometrically, how can I think of it? Any proposal? We have to find something in the upper half plane that G acts on, and its stabilizer has to be trivial.
The unit tangent bundle over H.
Yeah, right, great. So what we can do is we can take K, which is the stabilizer of a point, and we can further rigidify it by attaching to this point a unit tangent vector, say pointing up along the real axis. So B is in the tangent space at I to the upper half plane, and the length of the, which I'll just call this absolute value, should be equal to 1, oriented in the positive direction along this A axis. And when you apply K, you spin this vector around. When you apply N, you slide it back and forth along this horocycle. And when you apply A, you move it back and forth along this geodesic. And of course, by isometry, you can move the I to any other point in the upper half plane. And then afterwards or before, you can rotate so that this vector goes to any other unit vector. And once you know where this point and this vector go, you know the isometry completely. So G itself is isomorphic to the unit tangent bundle to the upper half plane. Okay, so we have these 5 homogeneous spaces, and all of them play significant roles in the theory, even though this is the one that we tend to concentrate on or think most about. Now, why do we think about H more often than these other spaces? Well, one reason is that H is a Riemannian manifold. It comes equipped with an invariant metric, and that's because K is compact. These other spaces do not carry natural G invariant metrics. If they did, then the homogeneous space, the stabilizer would have to be a compact group because the isometry is fixing a point, forming a subgroup of the orthogonal group. So these are not Riemannian spaces, the space of geodesics, the light cone, the unit tangent bundle, but they do mostly carry natural measures that are invariant under the action of G. But even that isn't always the case. The quotient by AN, that is the unit circle, doesn't carry any G invariant measure. So we can do ergodic theory for the action of G on these various other spaces, albeit ergodic theory of an infinite measure spaces. But here, we don't even have an invariant measure for the action of G. As you've seen several times, the action of SL2R on the circle has no invariant measure. Okay, so that's a panorama of the rest of the geometry of hyperbolic space and its connection with Lie groups and homogeneous spaces. And this discussion can be thought of as part of Klein's Erlangen program. Klein's idea was that geometry is really the study of a Lie group. It's not so much the study of this particular homogeneous space, and that the various subgroups of that Lie group correspond to various types of geometric objects within that space. And we're going to pursue that idea quite a bit as we discuss homogeneous dynamics. Okay, so now our next goal is to get to a place where we can do ergodic theory. And to that end, what we want to find are the subgroups gamma contained in G, which are discrete, such that the quotient of hyperbolic space by the action of gamma, let me call that X, has finite area. And maybe is even compact. That would be even better. And for example, it would be nice to find some concrete examples of hyperbolic surfaces. Hyperbolic surface is just a surface of constant negative curvature. If the curvature is -1, its universal cover can be identified with H, and then the quotient of H by the action of the deck group will give the original Riemann surface X. Now notice, and this is something it took me decades to learn, that I'm having gamma act on the left on H. And the reason I'm doing that is because H itself is the quotient of G by the action of K. So that actually makes sense. So X can actually be written as gamma mod G mod K. And you'll notice that there's a natural space that covers this, which is gamma mod G. And geometrically, G is the unit tangent bundle, so this quotient is nothing more than the unit tangent bundle of the Riemann surface X itself. Okay, so what properties does gamma have to have? Well, first, it needs to act properly discontinuously on H. So we want gamma to be discrete. And then, to make the quotient fairly small, we want gamma to be big, a large group. So the quotient has, say, finite volume or finite area. And then one thing we might require if we wanted surfaces is that gamma is torsion-free. If it's torsion-free and discrete, then it acts freely and properly discontinuously, and we really do get a covering map from H to H mod gamma. Now, it turns out that this condition, it's often good to ignore. That is, why not allow gamma to have some torsion now and then? all that will do is it will turn X from an ordinary Riemann surface into an orbifold. So it may have some orbifold points on it corresponding to points with non-trivial stabilizers, elliptic elements in the group. And it turns out to be very natural to allow these torsion elements in the group. And in fact, one could argue that we should really be working not with the space of orientation preserving isometries, but with all isometries of H, because that will allow us to put reflections into the group as well. And reflection groups are very important, and they also give quotients which are orbifolds. They're just not orientable. Okay, so my first step in describing such a gamma is going to be to discuss this 2, 3, 7 triangle group that we were discussing, looking at just a moment ago by shared screen. So any questions or comments before we proceed to this construction of hyperbolic surfaces? Okay, so I'm going to start with a goal that sounds slightly different from what I've written down here, but will still lead to an interesting gamma. And that is, I'm going to construct not the group gamma, which seems hard. How do you describe infinitely many elements inside of G? Instead of that, I'm going to construct the 2, 3, 7 triangle. So let's start by doing that. Let's construct explicitly 2, 3, 7. Now, why am I doing this? Well, you'll remember that when we wanted to discuss A5 contained in the isometries of S2, actually, this is very closely allied to constructing the 2, 3, 5 triangle on the sphere. And I think I forgot to enunciate this. In general, the angles inside of this triangle are pi over 2, pi over 3, and pi over 5. Let's call those A, B, and C. And you'll recall that what we need for a spherical triangle is that A plus B plus C is bigger than pi, and indeed the difference is equal to the area of the triangle. Well, the same thing happens in hyperbolic space. So the triangle we're trying to construct here will have area, again given by its angle defect, but the angle defect here, the sum of the angles will be less than pi. So the area will be pi minus, well, let me write it this way, 1 minus a half minus a third minus a seventh. Okay, now what does this sum come out to be? Well, there is a good way to do that without messing around too much with common denominators. Write this as minus a sixth plus a sixth minus a seventh. Okay, now we know this is a flat triangle. A half plus a third plus a sixth is 1, so this all cancels out. And we get pi times a sixth minus a seventh. Now we use common denominators to say this is pi over 42. This triangle turns out to be the smallest area hyperbolic triangle possible with internal angles that are of the form pi over n. And we'll, as we discuss this in more detail, we'll see that in fact it gives rise to the smallest quotient possible of the hyperbolic plane. So it's really some sort of canonical object. In the same way as A5 is the biggest group here, the reflections through the sides of this triangle, or its orientation for preserving subgroup, are in some sense the biggest subgroup that you can have inside of H. So that's to illustrate its importance. And as you can see, if we were to start replacing 7 with 8, 9, 10, the area would go up. And if we replaced it with 6, then it couldn't possibly exist. The area would be 0. Okay, so how do we construct this triangle? And by construct, I mean really, I showed a picture of it. How did I draw that picture? I had to literally find a triangle in the hyperbolic plane with the right angles. Now you could do this by a sort of ad hoc method, but let me give a somewhat more systematic and simpler method for constructing the 2, 3, 7 triangle. So what I'm going to do is, see, this triangle should have one vertex with an angle of pi over 2, which is 90 degrees. So why not normalize in the disk model so 2 of its sides are the imaginary and real axes going through the origin. Then I just have to construct one more circle, which is this circle C, and it should cross here with angle pi over 3 and here with angle pi over 7. Now, of course, at this point, you're reduced to some calculation in the plane, but I'm going to do it in the Minkowski model instead. So I'm going to write these circles, and excuse me if I get the indices interchanged. I'm going to write C1 as the perp of, actually, I think this is C2, and this is C1. Anyway, let me say C1 is the perp of the vector 1, 0, 0 in the space of geodesics. Remember, the space of geodesics is x, y, and t, such that x squared plus y squared minus t squared equals 1. So this certainly qualifies. It's a special case where t is equal to 0, x and y should in total have modulus 1. And then c is the perp of this vector. And then C2, we can take to be the perp of this vector. And then finally, C3 should have the property that its inner product with C1 and C2 gives these 2 other angles. So C3 should have the property that C3.C1 should be equal to, and remember, we have to put in some arrows here to get the orientations right. So it will turn out that this should be minus cosine pi over 3. And then C3.C2 should be minus cosine pi over 7. And we're almost done, because that means that this, the element of the light cone of the geodesic specifying this triangle, we know one entry is minus cosine pi over 3, the other is minus cosine pi over 7. And then the last entry, t, is completely determined by the requirement that this equation is satisfied. I mean, it's determined up to sign. Okay, and then from that information, as I mentioned last time, if we call these numbers x, y, and z, which I've now basically given to you explicitly, you can figure out what C3 is. So what C3 is the its center is at the point x over t, y over t, which is what this triple corresponds to when we projectivize. And then its radius, right, it's the places where this circle is crosses orthogonally the boundary of the unit disk, those are at, the radius is just 1 over t, as I mentioned last time. Okay, so that's how one can quite explicitly construct this 2, 3, 7 triangle. And then, as I mentioned, if you take this 2, 3, 7 triangle and you start reflecting it through its sides, then, for example, here at the origin, when you reflect it, you'll get 4 copies. They fit together nicely around this vertex because the angle is pi over 4. And similarly, when you reflect it around this vertex, because the angle is pi over 7, you'll get 14 triangles coming together, and so on and so on. So you can actually tessellate the hyperbolic plane by simply repeatedly reflecting this triangle through its sides. And that tessellation is invariant under some sort of group. what group is it? It is, in fact, the orientation-preserving subgroup of the reflection group generated by this triangle. So we then can let gamma be equal to the orientation-preserving subgroup of the group generated by reflections in the three sides of this triangle. And this will be a discrete subgroup of symmetries of the upper half plane, and its fundamental domain will consist of, say, any two adjacent triangles, any two triangles that share an edge. And therefore, it's discrete, and moreover, it's co-compact because it has a compact fundamental domain. Here's another way to think about this group gamma, which we've just constructed. So we built a particular triangle. We draw it like this. We built a particular triangle with angles 90 degrees, 60 degrees, and some weird pi/7 degrees. And this triangle is an element of, is a piece of a hyperbolic surface. Now let's just take two copies of this triangle and glue them together back to back. What do you get? Well, you get something that is actually a hyperbolic surface everywhere except at the vertices. Because when we take a point here, since we're gluing two copies back to back, on the back there's a corresponding semicircular neighborhood of the same point P. So when we glue together, we get a complete hyperbolic structure around every point on the edge. And at the vertices, when we double, we get not quite a hyperbolic manifold structure, but a hyperbolic orbifold structure. Locally, the double looks like the quotient of the hyperbolic plane by a rotation of order 3 or of order 2 or of order 7, depending on which of the cone points we're examining. So this object, the double of the 2, 3, 7 triangle, we can call that X. And it is nothing more than the quotient of the hyperbolic plane by this orientation-preserving subgroup I just described explicitly. One could also say, when you want to discuss a discrete subgroup of H, it suffices to build the quotient space. As long as the quotient space is a complete hyperbolic surface or a complete hyperbolic orbifold, its universal cover can be identified with H, and then pi1 of X becomes this group gamma. Now you might say, all well and good, but I really don't like these orbifolds. Could you please give me a good old manifold? This is a ridiculous example of a hyperbolic surface. It's not even a surface. And that's a good objection. So in fact, there is a subgroup of gamma. Let me call it gamma naught, which is torsion-free and has finite index. And that subgroup has the property that the corresponding quotient space is a surface of genus 3. So this is H mod gamma naught now. And what do you think the degree of the covering map is? Well, one way to figure that out is, I've erased my computation here, but we computed that the area of this triangle was pi over 42. So the area of this double is pi over 21. And then what's the area of a surface of genus 3? Well, it's the area is 2 pi times the absolute value of the Euler characteristic, which is 2g minus 2, So for 3, that's 6 minus 2, 4. So this is 8 pi. So what is the degree of this covering map?
Eight times 21.
Okay, what does that come out to be?
168.
Okay, can somebody else tell me where they've seen the number 168 before? And if you don't remember 168, you're also allowed to answer for 84.
Maximal size of the isometry group of a Riemann surface.
Right, exactly. So there's a famous theorem that bounds the order of the automorphism group of a compact Riemann surface of genus G. Remember, the complex analytic automorphisms are the same as the hyperbolic automorphisms. So there's a theorem that says the cardinality of the automorphism group of X is less than or equal to 84 times G minus 1, provided the genus is greater than or equal to 2. This is for any X is a compact Riemann surface of genus G. And sometimes this is proved using complex analysis or Riemann rock, that kind of tool. Here is a geometric instance where it turns out to be sharp. So there's this beautiful surface of genus 3 that has a huge group of automorphisms. And it's hard to say what that group looks like, but it's very easy to say what the quotient looks like. And so this surface of genus 3 has as a quotient by its full automorphism group this 237 orbifold. And the orbifold structure arises because automorphisms here can and do have fixed points. How do you prove this theorem? Well, it's very easy. You just look at this same picture. So in general, the area up here is 2 pi times 2g minus 2. What about the area of this quotient orbifold? Well, I wrote down a formula for the Euler characteristic of an orbifold. And the Euler characteristic of a hyperbolic orbifold has to be negative. And if you examine that formula, it turns out that to get the largest, to get the Euler characteristic as close as possible to 0, you, just as to make this group as big as possible, you need to use a half, a third, a fifth, because that's almost a half, a third, a sixth. To get this Euler characteristic as close as possible to 0, you have to use the 237 triangle. And so underlying this theorem is actually a simple fact, which is that it's a topological fact, which is that the Euler characteristic of an orbifold, a compact surface orbifold, is if it's less than 0, then this implies it's less than or equal to minus 1 over 42, and the equality is obtained for the 237 orbifold. Okay, so that's one simple example of a hyperbolic orbifold that can be given very concretely, and maybe a little less explicitly, an example of a compact, smooth hyperbolic surface of genus 3. Let me give you a simpler example for genus 2. So I guess we can just call this example 2. This is the construction using regular polygons. Now you might think I'm going to construct a regular octagon, identify opposite sides, and get a surface of genus 2, but I want to do something even simpler than that, which is this. if in Euclidean space, the interior angles of a pentagon are more than 90 degrees. But as you increase the size of a pentagon or any polygon in hyperbolic space, keeping it regular, the interior angles go to 0. In the limit, you get what's called an ideal pentagon. If you were to take a pentagon whose vertices are the 5th roots of unity, then it would be bounded by infinite geodesics. The vertices will have disappeared, the area will remain finite, and the interior angles will go to 0 because these geodesics are parallel. So somewhere in between, there is a right-angled pentagon. Of course, the sides have to be slightly curved in the Poincare model for them to come out to be right angles. So there's a right-angled regular pentagon. And as usual, this generates an interesting tiling, and we could look at a subgroup, et cetera, et cetera, et cetera. But what I want to do is simply use the existence of this right-angled pentagon to construct hyperbolic surfaces of every genus. Okay, so there's a little proposition here. And again, by using the Minkowski model, you can quite easily construct this polygon explicitly. There exists a regular hyperbolic pentagon. And I'm going to put the word right here. Right hyperbolic pentagon, meaning that the interior angles are right angles. And now, as a corollary, I'm going to say there exists a hyperbolic surface of genus 2. And here's the proof. So this is, in the old days, this is how people used to draw surfaces of genus 2. It's only in modern times that people learn to make it a little bit more plausible like this. And the idea was that, well, this is just the top view of the surface. And of course, there's on the bottom, there's more stuff. So you can think of this as you have this region here with 2 holes, and you glue another copy to it on the back, just like we did when we doubled the triangle. And now what you do is very simple. Let's just dissect this surface into some polygons like this. So this is all topological. So what I've done is I've taken the surface of genus 2 and I presented it now as the union of 8 cells, or 8 tiles, let's say. They're 2 cells with boundary, and the interiors are disjoint, and they cover the surface. Okay, now what are these cells combinatorially? Well, let's just count. 1, let me emphasize that the boundary is part of this. 2, 3, 4, 5. So combinatorially, they're hexagons. And if I make them right hexagons, then when 4 of them come together, they fit together neatly, just like the vertices of a square fit together neatly to form a torus. And similarly at the top, here you see 2 pentagons coming together. Remember, there's 2 others on the back. And so if I just take 8 copies of the pentagon that I just constructed and glue them together on the front, and then glue them to the same thing on the back, what I'll get is a complete compact hyperbolic surface of genus 2. So that gives a very concrete example of the existence of a hyperbolic surface of genus 2. So notice that the existence of a hyperbolic surface is almost trivial. In fact, Euclid undoubtedly knew that there exists a flat torus. Take a square and identify opposite sides. Probably he didn't think of these identification spaces, but intuitively, it's a very small step in Euclidean geometry to construct a flat torus. Similarly, it's very easy. It's like high school level geometry to construct a hyperbolic surface of genus 2. But now every surface of higher genus is a covering space of a surface of genus 2. For example, if you want to get a surface of genus higher than 2, you just take this surface and you unwrap it around one of its handles, and you'll get a surface that covers it, say with an abelian group of order Z mod 4 in this picture. There's an abelian cover of the surface of genus 2 that has genus 5. And similarly for every other genus, you just pull back the hyperbolic structure or pass to a subgroup of finite index in gamma, and you get compact hyperbolic surfaces of every genus. So there exists a hyperbolic surface of genus G, in fact, for any G greater than or equal to 2. Okay, now of course there's many variants of this construction, and I won't go through them all. I just want to illustrate how easy it is to get to concrete hyperbolic structures and thereby to discrete subgroups of PSL2R. How about some other examples of discrete subgroups or lattices in SL2R? Well, another type of example has been seen by everyone who's studied elliptic functions. Namely, inside of SL2R, there's the subgroup SL2Z. So there are so-called arithmetic groups, which are constructed not initially by geometry, but by algebraic considerations. And in particular, we can take inside of SL2R the 2x2 matrices with integer entries. And of course, this maps by degree 2 to our group G. And this group is a lattice, i.e. the volume of H1 gamma is finite. In fact, we can easily compute what the volume is, but it's non-compact. So the way this group is traditionally discussed in the theory of elliptic functions, as you all know, is you think of 1 and tau as forming a basis for a lattice. And now there's many other possible choices of basis for this lattice. And what you try to do is among all the different tau that specify the same point, you try to maximize the value of the imaginary part, or the height of tau. So what we can try to do is inside of gamma dot tau, we look in this full orbit for the point G dot tau with its imaginary part as large as possible. And that is how we construct a fundamental domain for the action of this group. So the fundamental domain consists of the region between plus or minus a half and the outside of the unit circle. We put the point I in here. Here's the cube root of unity. The fundamental domain for the action, a fundamental domain for the action of this group consists of this region here. And the way you get there is you just use, inside of SL2Z, you use the transformation Z goes to Z plus N, or I should say tau goes to tau plus N, and tau goes to minus 1 over tau. So if you're given a point tau somewhere, you first translate it so it lies between these two horizontal lines. Since these lines are distance 1 apart, since they're distance 1 apart, any point can be translated by an integer, so it lies in between those two lines. And now if tau happens to end up down here, inside of the circle, we apply this transformation, which is almost the same as reflection through the circle, to get a point outside the circle. And what happens is that the imaginary part goes up. But now you might be way outside of this strip again. So then you translate back. And if you're inside the circle, you reflect again. And eventually you land in this fundamental domain. So that's the proof that F, sketch of the proof that F is a fundamental domain for the action of SL2Z. And indeed, these generators, tau goes to tau plus 1 and tau goes to minus 1 over tau, they can be used to identify the sides of T. So tau goes to minus 1 over tau, glues this edge to this edge, and translation by 1 glues this edge to this edge. But what you see is that when you do this gluing, you're fixing this point here. So you create an orbifold point. So somehow SL2Z is starting to look a lot like the 2-3-7 triangle group. And in fact, maybe a better way to think of SL2Z is the following. Suppose I draw this geodesic here, which makes a right angle, and then this geodesic here, which is part of the fundamental domain, and then this edge here. Now I have the 3 sides of a triangle, just as I did for the 2-3-7 case. And I can tile the hyperbolic plane by reflecting this triangle through its sides. I can reflect over here. I can reflect down here. Sorry. And so on, and get a tiling of the hyperbolic plane. And then a fundamental domain consists of any 2 adjacent tiles, for example, this one and this one. So that's another way to think about the action of SL2Z. What are the angles of this tile? This is pi over 2, this is pi over 3, and what about at infinity? What's the interior angle between these 2 sides of the triangle?
Zero?
It's 0, right? These lines, these are asymptotic geodesics. So at infinity, they meet like this. They're parallel to one another. So the interior angle is 0, which is pi over infinity. So this triangle T is what's called the 2-3 infinity triangle. And so we can sum up this discussion with the following theorem. The quotient of the upper half plane by the action of SL2Z is the 2-3 infinity triangle, orbifold. In other words, it looks very similar to the case that we just did with 2-3-7, but now it's non-compact. But it still has finite volume. Its volume can be computed by orbifold considerations, etc. So this is what the quotient of SL2Z looks like. It's just a double of this very simple looking triangle. So that's another very concrete example of a lattice of central importance in SL2Z. I remember I once went to a talk by Dorian Goldfeld. He started the talk by drawing the fundamental domain, and then he said, this is the most important picture in mathematics. Time will tell. Okay, what next? Well, once again, you might object, I hate orbifolds. Could you please give me some manifolds, some hyperbolic surfaces, not these stuff with torsion? And in fact, there's also a very natural arithmetic way to do that. Namely, inside of SL2Z, there's a subgroup called gamma of n for each n. And it's just a set of matrices that are congruent to the identity mod n. So for example, gamma of 2 turns out to be generated by the matrices 1, 2, 0, 1 and 1, 0, minus 2, 1. These are both congruent to the identity mod 2 be congruent to the identity. It just means the diagonal entries are odd and the off-diagonal entries are even. It turns out that for n greater than or equal to 2, these are all torsion-free. So they give finite covers of this orbifold, which are honest manifolds. So let me just give you an idea of what some of those covers look like. So for example, gamma 2 maps here, and the quotient of H mod gamma 2 is nothing more than the triply punctured sphere. In other words, it's the double of a single ideal triangle. As a Riemann surface, it's isomorphic to the Riemann sphere minus 0, 1, and infinity. And the group of deck transformations is the symmetric group on 3 letters, which acts by permuting these punctures. When you cyclically permute the punctures, there's a fixed point of order with a stabilizer of order 3 on the top of this picture and another on the bottom. Those descend to give this point here. And then in the middle of each edge, there's a permutation that interchanges 2 vertices while keeping the other one fixed. So this triply punctured sphere, modulo its full automorphism group, gives you the 2, 3 infinity triangle. And in fact, this map is, if we think of everything as starting with the upper half plane, the map to this quotient is what's usually called J in the theory of elliptic functions, and the map to this quotient is what's called lambda. They correspond to the cross ratios of an ordered and an unordered 4-tuple of points. Now, what is this group S3 really? Actually, it's just the quotient of SL2Z by gamma of n. And we should really take PSL2 to get this right, because we're acting on the upper half plane. We always have plus or minus the identity in our group. So this deck group here is essentially the same as SL2Z modulo gamma of n. This is what you might call SL2 of Z mod n, or PSL2 of Z mod n. And it's the automorphisms of the projective line over this ring, or at least when n is prime, it's the automorphisms of the projective line over a finite field. So this group here can be regarded as PSL2 of Z mod 2. That's a way of thinking about the symmetric group on 3 letters. Well, it turns out that for gamma of 3, the quotient is the group that arises PSL2 of Z mod 3 is essentially the group A4. And the covering space is the Riemann sphere, but now with more punctures. These punctures come from the vertices of a regular tetrahedron. So in fact, the Euclidean solids are somehow hidden inside of SL2Z, and this maps with quotient group A, with deck group A4, again down to the 2, 3 infinity orbifold. And similarly, gamma 4 corresponds to S4, i.e. the symmetries of a cube or an octahedron. Gamma 5 corresponds to A5. But then you can keep going, which is really wild, because traditionally we think of the Euclidean solids or the Platonic solids as stopping at A5, as stopping with the dodecahedron. That's the most complicated they can be. But what happens is that when you try to go beyond 5, these Riemann surfaces continue to exist. It's just that their genus is more than 0. So the cases where you get the sphere are up to 5. For gamma of 6, you get genus 1. And for gamma of 7, remarkably, what you get is genus 3. And indeed, PSL2 of Z mod 7 that's the symmetry group of the projective line over the field F7, is this group of order 168. It's this famous simple group. And we've already seen it today. It was some sort of covering space of the 2, 3, 7 triangle. So in fact, the 2, 3, 7 triangle is also somehow hidden inside of SL2Z. And let me just say a word to illuminate how that works. So what happens is that we had our let me start from scratch, that we had our compact surface of genus 3, we call that X, and this mapped with this deck group of order 168 to the 2, 3, 7 orbifold. But what we're working with when it comes to SL2Z is the 2, 3 infinity orbifold. Well, there's an inclusion of this orbifold into this one. And the covering space here describes a subgroup of finite index here. So we can pull that back to get a subgroup of finite index in SL2Z. And that subgroup will correspond not quite to the surface X we started with, but X with a bunch of points removed. In fact, X with 28 points removed. And what are those 28 points? They are the pre-images of this point of order 7. So hopefully 7 goes into 14, 28 times, 24 times. And what's happening is that you can, if you take the pre-images of the points of order 7, they correspond to a tiling of this surface of genus 3 by heptagons, by 7-sided figures. And if you delete the centers of those tilings, you'll get this non-compact surface, which is the quotient of H by the action of the above cell. And of course, now there's an inclusion going this way, making the whole diagram cubed. Okay, so that was a bit of a panorama of different constructions of lattices in SL2Z. Let me see if there's any other particular cases I want to draw your attention to. So there's more details, I should say there's more details in the notes, but there's also linked underneath the donut of genus 2, there's a link to something called Notes on Hyperbolic Manifolds, and in there you'll find a much more thorough development of surfaces. I guess the one other thing I want to say in terms of these specific constructions is this. Here is a third way to try to construct hyperbolic surfaces. Let's think about, stop thinking about polygons and thinking about something a little bit more interesting called a pair of pants. I don't know if this is 3 or 4. It's the next one. Pairs of pants. So what is a pair of pants? It is a compact hyperbolic surface with a geodesic boundary. It is not complete. And the boundary, it has 3 boundary components, and the boundary components can be of various length. Oh, what makes you think, Professor McMullen, that such a thing even exists? Well, here's one way to build it. So suppose I concentrate my attention on the front piece of this picture. In fact, let me construct here geodesics, A, B, and C, that run between the cuffs. Since these geodesics have minimal length, they make angles of 90 degrees with each of these cuffs. I'm saying the word cuffs here, not you know, in principle, you should have 1 waist and 2 cuffs, but I'm going to call them all cuffs. So if a pair of pants with 3 cuffs of various geodesic lengths, if I cut along these three geodesics here that join the cuffs, what I'm left with is a hyperbolic hexagon. Right? This is just a six-sided figure with sides alternating between the cuffs and these geodesics A, B, and C. On the back, I have another hyperbolic hexagon. Well, if I had two copies of this hyperbolic hexagon, I could just glue them back to back and I'd get a pair of pants. So the theorem is that there exists a unique hyperbolic pair of pants for any L1, L2, and L3, all positive. You can choose the lengths at will and create a pair of pants. And here's the proof. So let's work in the universal cover. Let's take the preimages of these geodesics, A, B, and C. Upstairs in hyperbolic space will correspond to just ordinary infinite geodesics. So this is B, C. Sorry, let me make this bigger so you can see it. These are the preimages of B and C upstairs. And then what about this cuff here? That is a geodesic running between A and C. It's the path of minimal length between these two geodesics upstairs. Similarly, the preimage of another cuff is this geodesic, and the preimage of the third cuff is this one. And their lengths are, this is L3 over 2, this is L1 over 2, and this is L2 over 2. And here is my hyperbolic, is my hexagon H, upstairs in hyperbolic space. So to construct this pair of pants, it suffices simply to find three geodesics such that the distance between the geodesics are these three given numbers. The geodesics should not cross, and the distance between them in pairs should be pre-specified. So let me just, to simplify notation, call these distances D3, D2, and D1. Okay, now suppose I were to write A as we like to write geodesics, as Q perp. Maybe Q1 perp, where Q1 is a vector in the Minkowski model for the space of geodesics. And B2 as Q2 perp. And similarly C as Q3 perp. Then I would know what the matrix of inner products is. Qi dot Qj would have to be the matrix. The following matrix, it would be 1, 1, 1 on the diagonal, since the Qi squared are equal to 1 in the Minkowski model. They're on the one-sheeted hyperboloid. And then the off-diagonal terms give you the distances. So here we would have minus the cosh of D3, minus the cosh of D2, and minus the cosh of D1, and then symmetrically over on this side. So to construct these three geodesics explicitly is tantamount to showing that there are three vectors in Minkowski space with these inner products. But in much the same way as we prove the existence of an arbitrary spherical triangle, proving the existence of this pairs of pants just boils down to a determinant statement. All we need to prove is that the determinant of Q is negative. So what we note is that the determinant of Q is negative. This implies Q as signature 2, 1, and then this implies that the desired geodesics exists. Okay. So one way, yet another way to build hyperbolic surfaces is to first build pairs of pants and use those as tinker toys to assemble more complex surfaces. So for example, what can we do with a pair of pants like this? Well, one thing we can do is we can just double it across its boundary. So we can take this pair of pants with lengths L1, L2, and L3, take a reflected copy of it, and glue the two together. And then lo and behold, we've constructed a Riemann surface of genus 2, a complete hyperbolic surface of a given genus. And we have a continuous parameter now. In fact, 3 of them. We can change the lengths of these cuffs at will. And so we can get a 3-parameter family of Riemann surfaces in this way, not just a single example, as we were getting from the regular Pentagon. In fact, there's also some freedom when I do the gluing. When I glue this cuff to this cuff, I could also twist to the right or the left by a continuous amount. So there's also 3 twist parameters. And what we find is that using pairs of pants, we can create a 6-parameter family of Riemann surfaces of genus 2. And so a non-trivial theorem, but not that difficult, is that in fact every Riemann surface of genus 2 can be obtained in this way. And so the space of Riemann surfaces of genus 2 is naturally isomorphic to r plus cubed, which specifies the lengths of these 3 cuffs, cross r cubed, which specifies the lengths of these 3 tau parameters. And this construction is what are called Fenchel-Nielsen coordinates. The space we're constructing is what's called Teichmüller space. And in general, what this shows is that as a real manifold, Teichmüller space is isomorphic to a cell of dimension 6G-6. Okay, so that was like a super fast description of many different constructions of compact and finite volume hyperbolic surfaces. And what we're going to do next time is go on to study the geodesic and horocycle flows on the unit tangent bundles of these surfaces. That'll be our next level of ergodic theory and homogeneous spaces. Okay.